What are product and sum types? By the end of this episode, you'll know how to use these two concepts to create a very well-fitting model for your domain. My name is Eric Normand, and I help people thrive with functional programming. Data modeling is very important in functional programming, and product and sum types are a way of thinking about how our data is structured. And these things, product and sum types, together, they make up what's called algebraic data types. That's just a term that people use all the time. So I'm going to give a little scenario. So imagine we have some process workflow engine where we give people like a to-do list, a checklist of things to do, and when they do it, then someone else has to come by and approve it, that they did it correctly. And then just for safety, extra assurance, we have a second person check too. So when they check it, they either say it's approved or disapproved, or rejected, something like that. So there's a positive and a negative. And also we have to remember that before they approve it or reject it, we have to record that they haven't yet. Okay, so we actually have three cases, right? We have they haven't checked it yet, they have approved it, or they have rejected it. And then we have two of those because we want two checks. So if you look at all the possible states, we have 3 for the first one and 3 for the second one. Then there's all the combinations of the two, right? So the first one approves, the second one rejects. The first one approves, the second one approves. So there's all these combinations. How do you figure that out? Well, it's 3 times 3. So there's 9. But then when you think about it, what does it mean? These people are, they're doing the checks one at a time, right? So there's the first person's check and then the second person's check. And so you might have all these rules in your system, like if the first person rejects it, we don't need the second check. We're just going to tell them to do it again, right? So you need 2 approvals. And if you have a rejection from either one, so then you don't need the second rejection, right? If you have the first rejection. So what does it mean to have a rejection and then an approval? Because it's not even possible to get in your system. But what does it also mean for the first one to be not checked yet, but the second one is already checked? Because if they're going in order, that is not a valid state either. So what's happened is we've created this system where we've got 9 possible states, and it turns out that several of them are not valid. They don't make sense in our system. What does it mean for the second approver to check before the first approver has checked? What does that even mean? Because if they're second, then, or if they're first, if they come first, they should go in the first slot, not the second slot, right? And then what does it mean for someone to approve after it's been rejected? That also doesn't make sense. So if you do the math out, there's quite a few states in here that don't make sense. Now the math we've done, let's just go back to that. Math we've done is we've had 3 possible states, and we multiplied it by 3 possible states, we get 9 possible total states, right? We multiplied. And that's where the product comes from in product types. When you have 2 separate fields, and each one has a certain number of options, to figure out the total number of options for the 2, you multiply them together. And if you had a third one, you multiply that one together. You had a fourth field, you multiply those together. Okay? Now, that's the product, right? Because product is multiplication. Where does the sum come from? Remember, sum is plus. Well, the plus is that you have one unchecked plus 1 approved plus 1 rejected. You could have, as an example, you could have just a status of approved and rejected, and then that's a type. Okay, that's like an enum, right? So that's 2 states, and then to add a third one, you can make that a maybe. So you're adding the none case, the nothing case, by wrapping it up in a maybe or an option. Okay, so that's the sum type, because you're able to add one, you're not multiplying them. The classic, very, what do I call it? Essential product type is the tuple. The tuple is just a bunch of values. So if you have a pair, that's a 2 tuple. You can have a triple, that's a 3 tuple. And the tuple is a product type, meaning you multiply all the possible states together to figure out all the states that your tuple is in. Okay, and the typical sum type is something like an either, right? So either they approved or they rejected, right? It's an enum, right? All right, so the exercise that we have to do as data modelers is take this system that we've created, which we created poorly because there are states that are invalid in there that don't make any sense. And the thing is, if you're using a type system, the type system is going to say this is a valid state, because that's what you described. A tuple of 2 of these maybe statuses can be in any number of 9 states, in any one of 9 states, even though maybe 3 or 4 of them don't make sense. So you're not getting help from the type system to avoid those. How do you avoid them? Well, you're going to have conditionals in there to make sure that they don't happen. What kind of conditionals? Well, you're going to say, do we have some approval rating for the first one? Because if so, then we'll use the second one for this check that we're doing now. If not, we'll use the first one. So it's a conditional. The conditional is there because you've got invalid states. So you're adding complexity by having these invalid states. And what we want to do is use the sum and product types to rework this so that it doesn't have any invalid states. Just to get a little bit deeper into the problem that we had, like why did we get here where we have these invalid states? We broke the problem down, right? We said, well, each approver has a certain status, or they haven't done it yet. So that's 3. There's 3 possible choices for each one. And that's true of both. It's true of both. But when you combine them, it's not that the combination isn't a pure product, because there are states in that product that you don't want to be possible. So the problem was combining them with a tuple. And unfortunately, that happens a lot. I do it all the time, where I say, oh, I have 2 Booleans, and I'm trying to represent something with 3 states, but 2 Booleans is 4 states. And so then I have all this code to make sure I don't get into that weird 4th state that shouldn't make sense. So let's start with that 2 Booleans case. If we have 2 Booleans and we only need to represent 3 states, how would we do that instead? What else could we do? Well, 3 is a prime number, so you think, I can't do a product really, because a prime number is only a product of 1 in itself, and so the 1 doesn't make sense as a type. So what we do is then have to use a sum. So we just make an enum, or a sum type, and a union of the 3 possible choices. Instead of using 2 Booleans, we use 3 possible choices. Okay, so likewise, we could say, well, there's the case where no one has checked yet, the case where the first one has checked, and then the case where the second one has checked. So that's 3 cases. In the case where no one has checked, there's no other data we need to store, right? So it's just no one has checked. We could call that enum that. Then the case where the first person has checked is we have to capture what status they gave it. Did they give it approval or rejection, right? And then in the case where 2 people have checked, we have to capture both of them. So we capture the first one and the second one. Both are approval or rejection. And if you add that up, you have the 0 case, that's 1. The 1 person has checked, there's 2 possibilities there. So that's 1 plus 2, that's 3. And then in the 2 case, we have approved or reject twice. So that's 2 times 2, that gives us 4. So that's 1 plus 2 plus 4 equals 7. So that's 7 cases. Now, you could try to model more closely that once the rejection has happened first, like you can't have a rejection and then an approval. So we could say, well, in the 2-person case, we don't need to capture the first one anymore because that first one has to be an approval. We don't need to capture it, right? So we could call it, instead of the 2-person case, we could call it 1 approves, right? Or we could have a 0 have checked, 1 have checked and approved, 2 have checked and approved, and rejected. And we don't record who rejected it, whether it's the first one or the second one. Maybe we could. We could say rejected by the first, rejected by the second. Okay, so we're splaying out all the possibilities. So in this case, if we have 0 have checked, that's 1 case. 1 has approved, also 1 case. 2 have approved, 1 case. First one rejected, 1 case. And then second one rejected. So that would imply the first one approved. That's also 1 case. And how many is that? 0, first approved, second approved, first rejected, second rejected, that's 5. So that is probably closer to that's probably exactly fits what we want. Since 5 is prime, it's hard to do a product in there, but you could have a product where it's like 2 times 2 plus 1, right? So it's 4 plus 1, and somehow you have a 2 times 2 in there to get the 4. There's all sorts of possibilities there that we can explore. And the idea is you're using the structure of the product and sum to closely match, as closely as possible. You want to target exact the actual number of cases that you want to capture. Okay. When you talk about, well, there's 0 and then 1 and then 2, you might start to think we need something like a list. And I would explore that for sure. Not only because it makes sense, 0, 1, 2, but it also is like a more general data structure because, well, what if we want to change our process so we have 3 approvals necessary? Right? This is a way of making it the more general case, right? And of course, there's always a trade-off between getting very close and very close with like a huge type that you're developing that has all these constraints on it versus being maybe have a more general type that does have some invalid cases, but you work within the code to, with a few if statements to avoid those, and that might actually be cleaner. In a lot of cases, it it is. Sometimes the generality of it is actually better. But let's look at the list as a type. So lists are a sum type, and they're an interesting sum type. So the list is either an empty list or an element and a rest of a list. Okay, so the prototypical English words we use when we're talking about a sum type is either or, right? So you have either an empty list or the first element of the list and the rest. So or is usually used for sum types, and is usually used for product types. So the element and the rest of the list. Now notice the type is recursive. A list could have another list inside of it. And that's what makes it really interesting. So if you were just to do the math, let's say it's not recursive, it's two cases, a list or the head of the list and something else. But because it's recursive, that list could be infinite, in theory. There's no bounds to it. And so the size of this list now becomes, infinite. The number of possible states this list could be in. It's like it's unbounded in its growth. So that's another constraint on your system. Do you want to allow basically unconstrained growth? Because it's harder to make in a type system like this that we're talking about, it's harder to make a list of length 3 or 2 like we want here, right? It's harder to do that than it is to have an infinite list. Because if you want it to be length 2, you're going to have to just do checks to make sure it doesn't grow past that. But sometimes you want that. You want the underlying generality of, we don't know how many approvals we're going to want in the end. Okay, so it could be possible that you use a list. So you have the empty list. That means 0 people have checked. And then you add a check and a status. So that's the first element of the list, the only element of the list. And then you add a second one, and you add a third one, and you add a fourth one. All these statuses. And then you can do, it's another way of doing it. You'd say, well, if any of them are rejections, we reject it, right? Or maybe you could count them up and figure out a vote between do we approve or reject. You can do all of these things as opposed to modeling the transitions very precisely with the type. You're using more of a calculation to figure out how to whether to approve or reject that task. Okay, so these are all ideas in data modeling. I'm exploring this idea because I'm the third part of my book is all about data modeling, and I don't have a very organized view of what this chapter or this part is going to be about. What are the skills that people need to learn? But I think sum and product types are a pretty good way of being able to talk about what states are possible. A lot of languages don't have them in a strict way. They allow you to make them in a lot of times, but it's kind of a hack. So like in Clojure, we don't really have sum and product types in the sense that Haskell has them, but we do make tuples using vectors, and hash maps are product types because you have different values, and each of those values takes on different values, and so you multiply them together to get the total number of states possible. But we don't have enums. What we use is keywords usually if we need enums. So it's not it's not very straightforward in Clojure how to use them. They're more like idioms and patterns that we use. And likewise, in something like JavaScript, you basically do the same thing. You can use arrays to represent tuples, or you can use hash maps to represent tuples. How do you represent sum types? There's no enum, but you could use strings. You could use something like that. And you know, it's not the easiest. It's not the easiest thing to see, and that's why I want to teach people how to see this stuff. I learned this in Haskell. Haskell does it really straightforward, really clearly, and that's how I learned it. And I'm trying to teach it to people who don't have the opportunity to work in Haskell. Anyway, these are really important concepts. You have product types, which means you multiply the number of states to get the total number of states. The word in English that we use for product types is and. So you have the first status and the second status, right? And then there's sum types, which add the states together. So you might just add 1, you might add 10 other states. And the word we use in English is either or just either, or just or. It's either or because it's one or the other. It's not the or that has both inclusive or. It's either or, exclusive or. And those do a sum. Lists are a sum type, but it's recursive, so it's not just adding, because you're adding infinity to it. So it really explodes the number of possible states, which might be fine because you still have the two basic cases where I either have a list or I don't, and it's either empty or I have an element that is the first thing. And so that's how we use it when we process lists. We often do it recursively. All right. So if you enjoyed this episode, you can find all the past episodes at lispcast.com/podcast. There you'll find all of the old podcasts, the existing podcasts, with audio, video, and text. You'll also find links to subscribe, whether you subscribe with RSS, iTunes, YouTube, or just text RSS. And you'll also find links for finding me on social media, on Twitter, LinkedIn, email, etc. So looking forward to hearing from you. Thank you for listening. My name is Eric Normand. This has been my thought on functional programming. Rock on.